everybody, and welcome to another wonderful day of physical chemistry. So today we're going to continue our conversation on vibrational spectroscopy by bringing up a new type of potential we can use to describe vibrational motion. So last time we were talking about the harmonic oscillator, and the harmonic oscillator is essentially designed to be a good way of talking about vibrational motion near the bottom of the potential well. However, it makes a number of severe approximations. Most notably, it assumes that the restoring force for a vibration is equivalent in both directions. Whereas in truth, especially as we get to higher vibrational states, we have a lot of asymmetry in our vibrational well, which means we've got a lot of anharmonicity in our restoring force. So anharmonicity is essentially a way of saying that it's unbalanced. So a way to think about it is I've got a little bit more lax in a real vibrational system. I've got a little bit more laxness as I go to shorter distances until I reach essentially a sheer harsh wall, at which point I have a very strong restoring force pushing me away. And on the other end, I have essentially I essentially have a nice kind of long sloping potential, which means I have a much lighter restoring force when I go to larger distances. So essentially, I hit a harsh wall when I close into my neighboring molecule, and then I hit essentially a soft wall when I vibrate out. And you can kind of think of this as waves moving in an unbalanced pool. I bounce off the cliffside, come back and splash on the shore. Bounce off the cliffside, splash on the shore. And that's very different from essentially a nice spherical pool. And so we need to deal with several of these issues. First of all, this anharmonicity in our restoring force that's generated by our asymmetric potential. Second of all, we also need to acknowledge that our potential should essentially level off at long distances. So essentially, as I go to longer and longer distances, my potential will stop changing. And this is really what's going to allow molecular disassociation. We also want a potential that also has that sheer cliff face when we're bringing our molecules closer together. And it turns out there's actually a potential that fits this bill pretty well, and it's called the Morse potential. So our Morse potential is essentially given by a constant. The constant is typically given with respect in values of wave numbers, which then to turn into a potential, we have to correct by our good old friends HC. But our key feature here is actually going to be this exponential feature in the middle, which has a slow degradation offset by a value of 1. And the constant in that negative exponential has several key variables present. First of all, it has the effective mass. So this is, again, the same reduced mass we dealt with earlier. It also still has our vibrational frequency, and it also introduces this dE term again. Now, what this dE term essentially is going to be telling us a lot about is the depth of our potential well. So as a result, this is called the electronic dissociation energy or wave number, or a more general Morse constant. So what this is really going to be giving us is how deep our energy well is, which also tells us a lot about how much energy it will take for the molecule to completely disassociate if I start at a 0 in energy and go to where the potential levels off. So this actually has not just some equational meaning, but also some real meaning as well. And it's often a good indicator of bond stability. The other key feature I want to kind of emphasize here is the general shape of the equation. So we start off by having a square of the equation just to make sure that we always have a positive potential value. Then let's go ahead and look at this inner exponential. So if I have negative distances, which means that my two molecules are closing together, what we're going to see is that this would then give me a positive value in the exponential. So this value will increase drastically. And 1 minus this value, I'm going to have a very negative number, becomes very positive, and thus I have a well that quickly becomes infinite as that x value essentially increases. However, let's go ahead and take a look at what happens when x gets fairly large, so very positive. So this stays as a negative number, and then what I end up with is, as this becomes a very large negative number, the exponential will drop towards 0, and then I'll have a value of 1 here, and then my whole energy becomes HCDE, which again gives me the depth of the well. So essentially, how high is my potential barrier for my for my vibrating molecule to escape my potential well. However, one of the things that's important to note is that, well, DE is a measure of bond stability. It isn't actually the bond dissociation energy. And the reason why is because our molecule will never be present at the bottom of the well. Because remember, our system is always vibrating, which means we always have a ground state energy that we need to acknowledge. So in practice, what we can do is get our bond dissociation energy, which can be given by the 0 point frequency. So this is going to be the frequency of light required for our molecule to disassociate from the ground state. And this can essentially be given by taking the sum of our electronic frequency and the energy of the ground state. So by combining these two properties, this should give us the difference of these two properties should give us essentially the dissociation energy. And as a result, we can relate our two dissociation constant, the 0 point and the electronic, simply as by accounting for by subtracting out our 0 point free energy. However, this kind of begs the question, as we're going to need a little bit better of a way to try and analyze our energy levels in this Morse potential. So let's kind of take a look at what we might expect out of this system in terms of energy levels. So one of the biggest things that's worth noting is that when we go from a harmonic oscillator to a Morse potential, we're going to see our potential well widen out a lot. And as the potential well starts widening out, especially as I have this kind of reduced sloping barrier on the far side, this means that my energy levels will start to lower a little bit. And one way to think about this is that I've got to, as I go to higher and higher energy levels, I have a much wider well than I would expect. So more of that energy is going to be spent in movement, and less of it's going to be essentially forced to be going up. So essentially, we're going to have a slower vibration because I'm moving farther. In a harmonic, we expect fewer, faster vibrations. And one of the results of this is that at high vibrational levels, what we tend to find is, while the harmonic oscillator, they'll all be equally spaced all the way out. In the Morse potential, well, the volume between them starts becoming a little bit closer and closer. So we're going to tend to see it in our Morse potentials that these energy levels become very tightly packed as we get to fairly high vibrational levels. By the time you get to, say, an N of 6 or 7, they're practically all on top of each other as they've essentially spread out as the vibrations are now covering a much larger variance and a much larger distance than we typically expect from a harmonic potential. And again, what we're going to be seeing is that as we go to these higher levels, not only are we having this larger variance as I'm covering more distance in a real Morse potential system, but also you're going to notice that the center of that vibration also tends to move out and out. And this is actually a kind of a key feature. As I excite my bond to higher and higher energy levels, it's going to it's going to essentially slowly elongate until we get to kind of this logical conclusion. When I get to a high enough energy level, it can break completely as the uh, uh, as the average value slowly moves up. And this is, again, a key feature that we don't see with a harmonic potential. There is no way for a bond to break in a harmonic potential, and that isn't a real system. So if you're ever examining molecular dissociation, the Morse potential is going to be the way to go. However, we also need a mathematical way to kind of describe these energy levels. And it turns out that we use our favorite physics friend, we use a power series. So not too surprisingly, the first order solution for a power series is simply going to be the harmonic oscillator solution. So V plus 1/2 the vibrational constant. However, it turns out that we know the energy level should be slightly lower than this harmonic oscillator solution. And this comes up in the second order solution, where I'm going to reduce this potential by essentially the squared term of our vibrational constant plus 1/2 times what's called the anharmonicity constant times our vibrational constant. And so our anharmonicity constant is going to be kind of a measure of how wide the potential is. So essentially, if I know how wide my system is, I know how much my energy levels are going to be compressed. And it turns out, because of the way the Morse potential is structured, you can actually get at the anharmonicity constant through a ratio of our vibration, uh, the separation between our vibrational energies as given by the harmonic oscillator versus the overall depth of the well. So you know how deep the well is, you know the classical separation in between energy levels, you know essentially how much you've over predicted the system. So you can essentially lower this energy using the anharmonic correction. Now, it is true you can actually even use third and fourth order terms. For example, the third order term essentially says I overcorrected just a little bit with my second order solution, so I need to bump it up a little, and so on and so forth. But in practice, the second order solution gets our answers accurate enough, and this is the one that's going to be typically used. So again, first order solution is our good old harmonic oscillator. Second order solution includes anharmonicity, and we lower the potential a little bit to get these things right. However, it is worth noting that we're now talking about spectroscopy and not just potentials. So what I'm really going to care about is less about the energy of each individual level, and it's more going to be the separation between energies. And while it is going to be true when we go to the Morse potential, it's going to be a little bit more possible to go from, say, 0 to 2. These tend to be very kind of minor excitation. So most of our system will still be located at that, we'll be going from one state to the state directly above it. So we can essentially get the vibrational wave number for this excitation. We're going to give this value by taking the the ground state and adding 1/2. So for example, if I was looking at the excitation from 0 to 1, so ground state to first excited state, I'd give this the 1/2 term, 3/2, and so forth as I go on to further and further terms. Now I can go ahead and substitute in my my equations for each of these vibrational terms for both the first my starting state and then my excited state. So what we then see is I go from V plus 1/2, it becomes V plus 3/2. So again, I start at 1/2, I added an extra one, so V plus 3/2 times the vibrational constant, and the same expression for the anharmonic correction. And then we're just left with subtracting out the wave number of our initial state. Now, this next bit gets a little bit fun as I try and match up the math. So we have some easy terms. So for example, I know that if I take this first term of V plus 3/2 minus V plus 1/2, well, the V's are going to cancel. 3/2 minus 1/2 is just going to give me 1. So I'm just going to have my uh, vibrational constant. And you can think about it this way, that this first term is going to be just my harmonic oscillator solution. The second term is going to be due to the anharmonicity correction that comes from the Morse potential. So this one gets a little bit messier. We're going to need to do some expansions and some subtractions. But when you do this, what you find is that our vibrational, the excitation is going to happen at a slightly lower wave number than would be expected from the harmonic oscillator. And this is going to be based on several key features. First of all, the actual vibrational constant. Second of all, the anharmonicity term. And third of all, it's going to also be based on what the ground state we're exciting out of is. Because as we said, as I get to higher and higher vibrational levels, my energies become more tightly packed. So if I start at the ground state, well, then this is 0. I end up with 2 times my anharmonicity times the vibrational constant. So I take my original vibrational constant, I lower it just a little. By the time I get the heavily excited states, well, now this becomes, say, 3, 5, 7. It gets pretty big. And so as a consequence, our vibrational energy levels become a lot more tightly packed at higher starting vibrational levels. So as I excite out of a higher as I excite out of a elevated starting state, I'm going to find that my wave numbers are going to slowly drop off towards 0 until the point where it takes almost no extra energy to reach complete disassociation. So this kind of brings us to the general idea of the Morse potential. But again, I want to emphasize where the Morse potential really kind of falls into place. So one of the big things is that the Morse potential really shines when we're worrying about higher order vibrations. And this especially comes into play when I'm looking for descriptions of the disassociation of a molecule. It is going to be true that harmonic oscillator is going to be fairly accurate for excitations out of the ground state, but it is definitely going to fail when I start worrying about high temperature regimes and lighter molecules where I may have higher occupation of these excited states. One of the other important things is anytime you're looking for, again, anything with asymmetry, looking for the for a more accurate description of restoring forces, and most importantly, for that bond disassociation, you really have to go to the Morse potential. So that brings us to the end of Morse potential. Next time, talk about some rotational systems. Till then, take care.